you go down the pad? We'll marching right along. I guess last time we started by just sort of reviewing what's a polynomial, what's a root of a polynomial, what's the multiplicity of a root. And this led us to fundamental theorem of algebra, and that says that if you have a polynomial of degree n, it has exactly n roots, counting multiplicities. So if you do your accounting right, it has exactly n roots. And what that says is that there's really two ways, completely equivalent, of describing a polynomial. You can either write it in sort of the coefficient form, like this, or you can write it in the factored form. And different things are easy or hard, depending on which of the two data structures you use. So for example, if I ask you whether one polynomial is a multiple of another, this is the easiest way to do that. And so on. If I ask you to evaluate a polynomial at a given complex number, they're both relatively easy. Okay? Okay, so then here, of course, is a relation between these coefficients and the lambdas and the an. I guess the an is the same in both cases. There's a relationship, and one way is tedious but straightforward. In other words, going from this representation to this representation, you just have to multiply everything out and collect terms. Going the other way is called factoring. And last time I explained, gave you a little bit of historical background about factoring. And so I guess now you know that there is, in fact, a formula like the quadratic for the cubic, and there's also a formula for the quartic, although it's much, much, much less attractive, and there is none for the fifth and higher. Also, I think I finished by asking exactly what relevance that had to sort of current technology and factoring and polynomials, and the answer to that question was absolutely none whatsoever. So it's just a fun thing to know. But now you know that there's no formula for the roots of a fifth order polynomial in general. Okay. One more thing to mention here is almost always the coefficients of the polynomials we'll be looking at are real. And what's interesting about that is it means that whenever you have, if you have a complex number lambda and it's a root or a zero of the polynomial, so in other words, when I plug this in and just multiply out and add up this complex number, I get 0. It turns out that if I plug in the conjugate of lambda, you just work it out, you get exactly the same thing, you get 0. And that really says that whenever a complex number is a root of a polynomial with real coefficients, so is the conjugate. And so if lambda is real, this is a totally uninteresting statement. It says that whenever, for example, if 2 is a root of a polynomial, so is 2 bar, which is 2. It's not interesting. On the other hand, if the number is complex, it gives you another root for free. In other words, if you find that 1 plus j is a root of a polynomial, and so is 1 minus j. Again, this is all assuming the coefficients are real, which they are almost always, but in fact, not always. So there are cases where you actually have the coefficients are complex, and then this is all just not right. So people say that complex roots come in complex conjugate pairs. So in fact, when someone says, oh, what are the roots of that polynomial or something like that, people would typically say minus 3 plus 5 and 6 plus minus 5j. And so 6 plus minus 5j represents 2 complex numbers which are conjugates. So that's how it is. And it's often drawn as an example. I mean, as a picture in the complex plane. Here's an example of one. So it's drawn this way. You have the complex plane, and then the real roots, of course, lie along the real axis. So there's a root, there's a root. And then the complex conjugate pairs are symmetric with respect to the real axis. So if that's lambda 1, that's lambda 2, which is lambda 1 bar. And if that's lambda 4, that's lambda 5, which is lambda 4 bar, that kind of thing. So this polynomial here, by the way, what degree is this polynomial for this example? What's the degree of this polynomial? 6. And how many real roots does it have? And it has, yeah, so it's got 2 real roots, 2 complex conjugate pairs. Okay, so that's it. All right. Now, if you take the factored form of a polynomial, and then you collect together complex roots, and then also the associated complex conjugate root, you get this. Okay, so you pull together all of these. In other words, every time you have a complex conjugate here, a complex root, you pull together, you get its complex conjugate as well. And you write these as these pairs, which are quadratics. Now, we can actually multiply this out here, and what you get is s squared minus lambda I s minus lambda I bar s, and then plus lambda I times lambda I conjugate. Okay? Now, what is lambda I times lambda I conjugate? That's its magnitude squared. It's this, right? And this, when you have lambda I plus lambda I conjugate, that's twice the real part because the imaginary part cancels. And what that says is that those little quadratic terms that look like this can be simplified. You can write them as s squared minus twice the real part plus lambda squared. Now this, by the way, should tie in already to your intuition about second-order systems. Because for second-order systems, you'll remember that it was b squared over 2a, a is 1 here, that determined kind of whether or not the roots were real or imaginary, and it gave you that damping term. That's exactly what this is here. It's the real part. And so that says that we can write a polynomial in the so-called real factored form. What you do is you express all the real roots this way, like that. So these are just so here the coefficients, the lambda i's are all real. Every time you have a complex form, a complex conjugate root pair of roots, you multiply them together and you get a quadratic which has real coefficients. So alpha I and beta I are real. Okay. So what's interesting about this is as you can take any polynomial at all with real coefficients and you can factor it into a bunch of polynomials which are either degree 1 with real coefficients or degree 2. And in fact, this is going to turn out to be exceedingly important. It's going to basically tell us the following. It says that once you understand, it's going to explain why we spent a bunch of time on second-order systems. It says once you understand second-order and first-order systems, it's because of this result here that you're going to find out that you actually understand 17th-order systems. Because you can factor polynomials of any degree, for example, 17th order, you can factor it into a product of quadratics and single first-order terms. Okay? And so that's going to be the significance of this later. Okay, so let's just do a quick example here. S cubed minus 1, well, we know the roots of that. First of all, s equals 1 is obviously a root. You divide it out, you get something else. Here you write it out in, this is full factored form. If I multiply out this term and this term, I get this. I get s minus 1 times s squared plus s plus 1. And this is the so-called real factored form here. Okay. All of that was nothing but a precursor to our study of rational functions. This is really what we're going to be interested in. So a rational function is a ratio of two polynomials. That's what it's just a ratio of polynomials. So it's got a numerator polynomial, b, divided by a denominator polynomial, a. And here, the only rule is that this denominator polynomial should not be identically 0. In other words, it can't be the 0 polynomial. That's a rational function. And in fact, you've already seen them, a bunch of them. In fact, you've already seen a bunch of them coming up in Laplace transforms. Right. So here you call b the numerator and a is called the denominator. Here's some examples. 1 over s plus 1, that's 1. Any polynomial is a rational function because you can write it as itself divided by 1. 1 is also a polynomial. So every polynomial is a rational function. Any constant is a rational function. Here's another one. You can take 1 over s squared plus 1 plus s over 2s plus 3. And if you multiply it all out, you get a ratio of two polynomials. And in fact, it should be pretty clear that for rational functions, they are closed under addition and subtraction, multiplication, division, except you can't divide by the rational function 0. So in other words, this is, I guess, what we call a field. That's the technical term for it. It's like the real numbers or the complex numbers. In other words, you have a way of adding and subtracting them. You know how to multiply them. You can divide them, except you're not allowed to divide by 0. So this is called a field. So, I mean, not that it matters, but this is what it's called. That's very, very interesting, actually. What it says is that a lot of what you know will extend, in fact, to rational functions. That's what it says. A whole lot of what you know will extend. Just like complex arithmetic, it's not that hard to learn about complex arithmetic once you know real arithmetic because most things are pretty much the same. And then the only other thing you really have to concentrate on are, the handful of things which are different. For example, what does e to the j theta mean, right? It's totally unlike anything with real arithmetic. Another comment about rational functions is that when you express a rational function as a ratio of polynomials, the ratio is not unique. I mean, for one thing, there's the obvious thing that if I write 1 over s plus 1, I could multiply top and bottom by 3, and I get 3 over 3s plus 3. And these are, in fact, the same rational function. But people take a step further, and in fact, this rational function is the same as that. And let me explain why. Hey, wait a minute. Oh, that's fine. I multiplied top and bottom of this one by s squared plus 3. Okay? So here, in other words, b and a have a common factor, actually two common roots, plus minus j squared 3. That's this term and this term. Okay? Now, these functions, technically, depending on how careful you want to be, they're not exactly the same. For example, if I walk up to you and I say, what is the value of this function when s equals j square root 3? You would say, I don't know, what's the big deal? It's 1 over j squared root 3 plus 1. On the other hand, if I walk up to you and I say, what is this function evaluated at j square root 3? What would you say? Yeah, I mean, it'd be very complicated. You'd depend. First, you'd evaluate the numerator and you'd get 0. You'd evaluate the denominator, you'd get 0. Then you'd attempt to divide 0 by 0, and you'd come back with undefined. Or depending on how smart you were, you could say, oh, but I realize that these are, if you canceled these first and then evaluated it, you'd be fine. So in fact, these details people don't, you don't really worry about, and it won't matter. Okay, so rational functions. Poles and zeros. So you write a rational function out. We're going to assume that we don't have this pathology where the numerator and denominator have a common factor, because if they do, we could just as well cancel them. Okay. Now, in practice, in fact, determining whether or not a ratio of two polynomials has a common factor is not that easy. Okay. But we're just going to assume that if there is a common factor, it's been divided out. So the roots of the numerator are called the zeros of the function, of the rational function f. Why? Because when you plug in these complex numbers, you get f of a 0 is equal to 0. It's the zeros. Now, the roots of the denominator are called the poles of the function. Okay? And roughly speaking, these are the complex numbers for which f is equal to infinity. That's what it says. In other words, if I asked you if the number lambda is a 0 of this denominator, and therefore not a 0 of the numerator, why couldn't it be one of both? Precisely, right. There's no common factors, right? So if lambda makes this denominator 0, it does not make the numerator 0 by this assumption here, right? So therefore, if I say, what's f of lambda? It depends. But what happens is, as you're parsing this or evaluating this, you say f of lambda is, you get some complex number divided by 0. And in fact, a reasonable answer, which in fact is perfectly okay in this case, is to say that's infinity. You can call it undefined if you like too. It works either way. But here you can just say it's infinity. You can't say plus infinity. It's actually the complex infinity, which is a different thing. So you just say it's infinite. So the zeros of a rational function are the complex numbers for which it vanishes. And the poles are the complex numbers for which f is infinity or undefined. And this, you extend this to talk about the multiplicity of a 0 or a pole. So that's how that works. And the basic idea is something like this. If lambda is a pole of this rational function, then when I actually evaluate f of lambda, I get something over 0, which is infinity. If I plug in a complex number which is really near to a 0, but not to a pole, and not equal to a pole, what does f come out to be then? This is another way to understand what a pole means. What if I plug in a number that is which is close, but not exactly equal to a pole? Then what is this denominator in that case? It's small. It's not 0. If it were exactly 0, that number would have been a pole. But it's not a pole. It's near a pole. It's near a pole. This number is really small complex number. This one here is just some complex number. So I have a complex number divided by a really small, really small complex number. And what's that? It's a really big complex number. So a very good way to understand what's happening with f is to think in terms of sizes. If you want to avoid issues of infinity, you just say, well, look, to say that f has a pole at -3 means that if you plug in the complex number s equals minus 2.99, f of that number is defined and really, really big. So that's one way to think of it. Okay? So that's the idea. Okay. Well, now, again, using what we know about polynomials, we can do all sorts of stuff. We can do the factored or pole zero form of f. Oh, there's a question.
Yeah. Do you have a pole at s equals infinity?
Can you? Yes, people do talk about that. We won't, but people do talk about that. Yeah. For example, a polynomial is said to have, well, just here's a rational function, s. Okay? Just s. Then you say, well, what is it for near s equals infinity? People would say, well, I don't know. Near s equals infinity means s really, really big. And then what's s when s is really, really big? It's really, really big. So at s, people would then say that the rational function s has a pole at s equals infinity. We won't need to do that. By the way, when you do that, what do you think you could say about, what does that have at, I don't know, what does 1 over s have at s equals infinity? It's a 0, right? So there is a way to do all this accounting. For people who care, there's a consistent way with the complex numbers. Yeah, that's going to be a small fraction of us. But for people who care, there is a consistent way, in fact, to do complex arithmetic, where infinity is not an exception to be avoided, but it's just another number. And it works everything works out perfectly well. It's totally self-consistent. And I think that in that self-consistent system, what you said is exactly right, that you talk about poles and zeros at s equals infinity. We won't do that, but there is a way to do that. It's very elegant and very abstract and looks very sophisticated and not that useful for us. So, oh well. Okay. So we can take a rational function, a ratio of two polynomials, and if we factor the numerator and denominator, we get something called the factored or the pole zero form. It's called the pole zero form because if I ask you what are the poles and zeros of f, and I give you this, if this is the data structure I use to describe f, it's not easy unless this is, for example, a quadratic over a quadratic. Okay? On the other hand, here, these are the zeros, these are the poles, and so here I even have written it in a mnemonic form where I've called these z1 through zm and p1 through pn. Okay? So these are the so-called poles and zeros, and that's the idea. And of course, you have the same thing. You inherit this from polynomials, that if you have a 0 which is complex, the conjugate is also 0. If you have a pole which is complex, so is the conjugate. It's also a pole. So this is, you can also then do things like you can have the real factored form. For example, you can collect the zeros into pairs if they're complex and the poles, and this kind of just goes on and on and on, which I won't bore you with. Now, rational functions are described in a graphical way, which you will actually use from now on. I mean, not just in this class, but in every other electrical engineering class. And a lot of classes in mechanics, mechanical engineering, electromechanical systems, all sorts of things use this. And it's the idea of a pole zero plot. And here's the way it works. You plot the poles and zeros of a rational function by drawing a circle that's a mnemonic for a 0. Everywhere in the complex plane where you have a 0. And then you draw an X or a cross everywhere you have a pole. Okay? And so I guess this is, I don't know, not unlike some of these, I think in physics and stuff like that, when you're looking at a magnetic field or an electric field, sort of, isn't this the mnemonic for things coming at you and away from you or something like that? Anyway, so that's it. So this picture here shows a rational function whose numerator degree is 3 because there's 3 zeros, and whose denominator degree is 3 because there's 3 poles. Okay? And you could work out what it is. For example, here, to go from this plot to what the actual rational function is, you collect, for example, the zeros. And the zeros are at minus 1.5, and then I guess this is minus 1 plus minus 2j, and so I've got these 3 terms here. In the denominator, I've got these guys. I think I did it right. Did I? Oh, I did. Okay, it's fine. Sorry, you know what? There's actually 4 There's actually 4 poles. I'm sorry, I didn't see this guy over here. There's 4 poles. And so there's one at minus 2.5, and that shows up here. And you multiply it out. So this picture corresponds to this. Now note that a pole zero plot doesn't tell you this kind of gain, this overall thing in front, which is, well, we'll see later is called a gain constant, or so it gives you almost everything, right? So it's not unlike walking up to someone and saying, I'm thinking of a polynomial, and its roots are, and then you list the roots. You haven't actually completely specified the polynomial, because you could multiply that polynomial by 7 or 12 or minus 15, and you still get the same set of roots. This is the same kind of thing. Okay. So here you have to be able to go back and forth from a rational function described in many, many different forms to pole zero plots. You have to be able to do that going back and forth. And that's, of course, nothing but a matter of factoring and so on and so forth. Okay. Now I want to point out that so far, although this is surely very interesting and fascinating, but just to be totally honest here, I haven't told you yet why on earth you should be interested in rational functions. Right? We'll get there, but so far that's the reason we have pole zero plots is because soon this is going to mean an enormous amount to you. When you see this, you'll say, "Oh, okay, I know how that works now." Okay, when there's a circuit or something like that. So that's well, I thought I'd just insert that there because we're okay. Partial fraction expansion. There's lots of ways to write down. Rational functions. You can write it as a ratio of 2 polynomials, and then in fact you have choices as to how you represent the numerator and denominator. Do you write them in this form? Do you factor them? Do you put it in real factored form? Who knows, right? There's another form for a rational function which is going to be exceedingly useful to us, and that's this. It's the so-called partial fraction expansion, and it looks like this. You write it as a sum of rational functions, each of which has a constant numerator and a first-order denominator. Now, this actually only works when the poles, or the roots of this polynomial A, are all different. They have to be all different. You can't have repeated poles. Okay? So we'll look at that later. But this is it. Now, what's interesting about this is this is sort of like, I don't know, one of these canonical forms in logic or something like that. That there's a couple of different canonical forms, and they're useful for different things. For example, if I had written this out as this thing, s minus z1, when I write it out as the factored form like this, s minus p1 up to s minus p sub m, this, p sub n, here I'm really effectively writing the rational function as a product of rational functions with simple numerator and denominator. Here, I'm writing it as a sum, and it's different. So here it is. It looks like this. That's called the partial fraction expansion, and these coefficients in the top are called the residues. These are called the residues, and that's a history that goes back 150 years. So these have been looked at for about 150 years. So these are called the residues and the poles. So you can say, for example, in a partial, this is basically another data structure for rational functions. So someone could say, well, here are the residues and poles. And then you have to ask all the natural questions that come up when you talk about multiple data structures to describe one object. You have to say, can you transform between the two data structures? How would you do that? What's easier to do with one data structure than another? These are the types of questions you would ask. So here, whenever the pole is complex, the corresponding residue is also, and whenever lambda I is equal to lambda j bar, in other words, they form a pair, the residues are also have that property. So they're also conjugate symmetric. So let's look at an example to see how this works. Here's s squared minus 2 divided by s cubed plus 3s squared plus 2s. And the claim is, you'll be able to do it by the end of this lecture, that you can write this in this form. Okay? So right now, I'm not saying that anyone here should have even the remotest clue how I went from this to that. But surely everybody here could go from this to that. That's easy because that's elementary algebra. You put basically, to go from partial fraction expansion to the more conventional ratio, you simply put everything on a common denominator. So what I do here is the common denominator is s plus 1, s plus 2, and I have minus 1 times these two guys, product s plus 1, s plus 2, that's here. Then I have plus s times s plus 2, that's this term. And then finally I have plus s plus 1, that's this. And I multiply all this out, I collect like terms and all that, and when the smoke clears, I guess I probably do get, hopefully I get s squared minus 2. Okay, now, finally, I'll tell you why we're interested in any of this. It has to do with Laplace transform, and specifically inverse Laplace transform. If I gave you a rational function, if I just walked up to you and I said, what is the inverse Laplace transform of that? Your reaction right now would be, I don't know. How would I know? Right? Or you might look in that table that we handed out, that little table, and you wouldn't find it there. And then you'd say, well, I don't know. And you'd even look in a book. And you know what? You could get a big, thick book of Laplace transforms and inverse Laplace transforms. You wouldn't find it there. It's not there either. Okay? On the other hand, now that we know this is a fact, that this is equal to that, and I said, what's the inverse Laplace transform of that? Now it's easy. And in fact, you could have answered this a week ago. Easily, because you take the inverse Laplace transform term by term. That's minus 1. That's e to the minus t. That's e to the minus 2t. And not only that, it's extremely easy to do. Okay? So now we've done something that was useful. In other words, writing this form is actually useful because now, when you look at this, you can say immediately what the inverse Laplace transform is, well, provided you know how to go from here to here, which you don't yet, but you will. This is getting complicated, isn't it? Okay. So the inverse Laplace transform of a rational function in partial fraction expansion is extremely easy to compute. You just do it term by term. Now the implication is amazing because it says that if you know how to put a rational function into partial fraction expansion form, you know how to find its inverse Laplace transform. This puts you in a very, very good position. It says you will now have very, very good intuition and, for that matter, computational ability to compute the inverse Laplace transform of any rational function, okay? Which is gonna be very, very useful. Okay, so everything comes down to how do you transform from this data structure to that? How do you do this? Okay, well, a couple of things you need. I mean, obviously, if you look at the partial fraction expansion, all you really need to do is produce the poles and the residues. Now, producing the poles is easy. To produce the poles of a rational function, you simply have to factor the denominator. Okay? So we talked about that at great length last time. Okay? So you have to factor the denominator. That's not a mystery. Once you've found the poles, you have to find the residues. How do you do that? Well, let's take a look at this. So here is at a high level, what's involved in finding the partial fraction expansion. You have to find the poles, which is to factor the denominator. That's easy. And then you have to find the residues. And there's a bunch of methods to do the residues, a whole bunch. I'll look at a couple of them, and after a while you'll get the idea. The amazing part is that some of these the methods, although they all get exactly, of course, the same answer. I shouldn't say of course. In fact, it occurs to me I haven't said something important here. The partial fraction expansion is unique. I didn't say that here. I wonder why I didn't. Oh well. So the expression, I should make a note of that. Can you make a note of that, Leo, and I'll add it to the lecture somewhere. So here, when I write down a rational function as a ratio of two polynomials, that's not unique. We already discussed that. I could multiply top and bottom by minus 3. You get the same thing. But when I write down the partial fraction expansion, the r's and the lambdas are unique. Two people cannot get the different answers, period. You cannot have an argument about what the residues and poles of a rational function are. You can have a reasonable argument, it's a stupid argument, but you can have an argument about what the numerator and denominator of a rational function is. In other words, if someone else is doing homework 3 and you're doing the same thing and you look at it, you can actually have a different numerator and denominator, but they better be multiples of each other, right? So, okay. I don't know that this really matters or anything. Okay, so let's look at some methods for finding the residues. We're going to do everything for the case where the numerator is degree 2, denominator degree 3. Why? Because if I write out the general case, it will be very, very unattractive. That's why. So it's left to your imagination to imagine when it's unattractive here, how unattractive it is when the numerator has degree 6 and the denominator has degree 12. Okay? So that's going to be left to your imagination. So here's our problem. We have a rational function. To find the poles, we had to factor the denominator, and I did that. Here they are. These are the poles, lambda 1, lambda 2, lambda 3. I have a quadratic numerator, and I want to write this in this form. Okay? I don't know. I know B0, B1, B2. I do not know R1, R2, R3. I know lambda 1, lambda 2, lambda 3, and this is what I have to do. So let's clear denominators, and if I do that, and I get the denominator of, or I multiply both sides basically by this denominator here, I get, this turns into a polynomial equation, and it looks like that. Well, to say that two polynomials are equal says that the corresponding coefficients are equal, so what does that mean? Let's equate coefficients. The constant, the linear, and the quadratic term. And when you multiply all this out, like for example, the s squared term here is you get R1 plus R2 plus R3 over here, and over here you get B2. I get this set of equations. Okay? Now, all you have to do now, remember what you know here. You know B0, B1, B2. You know lambdas, and you don't know the r's. So if you stare at this long enough, you will realize you have a set of 3 equations in 3 unknowns. That's R1, R2, and R3. Okay? So usually, that means you can solve for them. And in fact, for those of you who've, I guess most of you have seen a little bit of linear algebra or something like this. So if the matrix here, if the corresponding coefficient matrix is non-singular or has non-zero determinant, that tells you that you can solve R1, R2, R3 from B0, B1, and B2. Okay, now it turns out in this case, that coefficient matrix is always non-singular, so you can always do this. Now then, the question of how do you find R1, R2, and R3? And actually, for a 3x3 system, it's not fun at all. So actually, do they still in math courses? They show you like what Gaussian elimination is or anything like this? Okay. Yeah. Okay. All of that is essentially useless. It's very interesting and totally useless. You didn't spend more. Did you spend more than 15 minutes on Gaussian elimination? 2 weeks. Okay. The correct amount of time, 15 minutes. The reason is, I'm sorry to be the one to tell you these things, but somebody's got to do it. Yeah. Yeah, I mean, the reason is that linear equations are basically, except if there's 2 equations and 2 unknowns, those are solved by people. Okay? 3 and up, these are solved by computer. And they don't even use Gaussian elimination. They use something like Gaussian elimination, but in fact they don't use Gaussian elimination because Gaussian elimination works kind of badly, right, in practice for having to do with like round off, and round off errors actually accumulate. So anyway, sorry to tell you that, but however, it is important to understand sort of the theory and how linear equations work. So in principle, you could solve this, but I think, how many people here have actually solved by hand a 3x3 set of a linear system? I mean, everyone should do this once. This would be like writing one assembly language program. You should do that exactly once and never again. So that every other time when you compile something, you can think back and understand and know what it is. So same in MATLAB. MATLAB will solve 3x3 and 30x30 and 300x300 sets of linear equations for you very, very quickly and very conveniently. And you should have done, so I'm glad you all solved the 3x3 system once so that you understand now that it was useless and that you'll never do it again. Kind of like writing assembly or something like that, unless you go into some weird line of work. So I don't know. Anyway, okay. All right. Actually, so how many people enjoyed solving 3x3 linear equations? Right. Okay. That's great. Oh, okay. All right. Well, it is. I mean, it's relaxing, and I don't know. It's yeah. Really, you should try 4. If you liked it, though, you can try 4x4. Because yeah, the pain goes up actually like the cube of the size of the equation. So gives you an idea. Okay. So let's just have a summary of this method. Summary of this method is actually, if you enjoy solving 3x3, 4x4, and 5x5 sets of linear equations by hand, this is your method. This is the preferred method for finding the residues, partial fraction expansion. Okay? Now let's try method 2. Here it is. We start with, I mean, this is all we're trying to do here is find, oh, well, here, sorry. There we go. That's what it looks like. No, it's all messed up here. All right. Here's what we're going to do. We're going to start with, here, the uncorrupted form. We start with this. All we want to do is find complex numbers, R1, R2, R3, such that this is true. What we're going to do here is we're going to multiply left and right-hand sides of this equation by s minus lambda 1. Okay? So when we do that, we get this. I multiplied s minus lambda 1 here. When I multiplied this term by s minus lambda 1, the denominator went away. Here I get that, and I get that. Now, this is much less attractive than what I had before, so you might ask, why am I doing this? Here's why. This says this rational function is equal to that, and I want you to plug in the following number. Well, first of all, let's cancel this. And now let's plug in s equals lambda 1. Well, when I plug in s equals lambda 1, what does this thing do? It's 0. Now, by the way, how do I know lambda 1 is not lambda 2? That was my assumption, remember, from the beginning. You don't have a partial fraction expansion unless the poles are distinct. So this term just goes away. It's history. It's history. And this thing here becomes, uh-oh, it just pops out. In fact, what I have is just a formula for R1. Okay? Now, this is, in other words, it's an analytical solution to this 3 by 3 set of linear equations. That's what it is. And it's not that bad. There it is. It's just an explicit formula. This is, this is what we like. What we want is over here on the right. On the left is a whole bunch of stuff, all of which we know. So there we go. Now, and you can do exactly the same thing for R2 and R3. And the general rule is you have this formula here. And the formula, you have to be a little bit careful about this, right? The correct interpretation of the formula is maybe here. To make it really pedantic, you put brackets around that. It says you take the rational function, you multiply by s minus lambda k, where lambda k is a pole. That's what you do. What happens is, since this is a pole, s minus lambda k appears now in the denominator and the numerator, and you have to cancel it. After you cancel it, then you plug in s equals lambda k, and you're going to just magically get the residue. Okay? So let's do an example. Here's a rational function. You look at the denominator. The poles are distinct. It has a partial fraction expansion. I write out the form. This is step 1. You just write out what it is. It's this. Okay? Now, to find R1, I multiply. In fact, you can even do this in your head. So that's in fact not a bad way to do this. It's the way I do it. So you have this. You want to get R1. Well, what do? You multiply both sides of this equation in your head by s. So this goes away, s, s, s here. Now, you do this. You get rid of that. Now you plug in s equals 0 into this expression. And what happens? That's gone. That's gone. Okay, whoops. And this is minus 2, because s is 0. It's minus 2 divided by 1 times 2, otherwise known as minus 1, I think. And that is, in fact, the residue. Okay? And anyway, so you repeat, and you get R2 and you get R3. And so in the end, you get, this is alleged to be the partial fraction expansion. Now, of course, once you've done this, especially if your reliability is as low as mine, it's extremely important to actually check. And so to check is easy. To check is algebra. You multiply this thing out, and if you don't get that, you go back to square one and you find out which residue is wrong or right and all that sort of stuff. That's the way that works. You should always check these things in the end, just to make sure it's right. Okay. So here is another method, which is also, it's completely explicit and useful expression for the residue. The kth residue is simply the numerator divided by the derivative of the denominator at that point. And if you want to know why, it works this way. That from our formula above, the way to get Rk is to multiply s minus lambda k by, well, the rational function by s minus lambda k, and then evaluate it at s equals lambda k. That's the same as sort of letting s go to lambda k, like this, right? Because that'll cancel that. Well, let's see. What is that? What we have here is a ratio of two things in a limit, both of which in the limit are 0. So we use L'Hopital's rule, which is to say that we replace each of these with their derivative. And you get this in the numerator, that in the denominator. When s goes to lambda k, this term happily and gracefully goes to 0. You get b of lambda k, and down here you get a prime of lambda k. Now, by the way, what if a prime of lambda k were 0? What would that mean? I mean, aside from the fact that this formula would then be a little bit problematic. But what does it mean if a prime of lambda k is 0 in terms of the original, right? So what's a of lambda k? What's a of lambda k? Lambda k is a pole of b over a. So what's a of lambda k? It's 0, okay? And if I told you that a prime of lambda k was also 0, what would that mean? If I have a polynomial, and I plug in a complex number, and you get 0, it's a root of the polynomial. And if the derivative of that polynomial also vanishes, no, not necessarily. No, not identically 0. It means its multiplicity, it's got a second root at that complex number, right? And so what it says is, if a prime of lambda k were 0, that means that it has a second pole at that complex number. But we ruled that out. The whole assumption here is that all of the poles are different. You cannot have two poles at the same complex number. Okay? So if you didn't follow any of that, you could just put a little note there that says a prime of lambda k is non-zero since poles are distinct or something. Something like that if you wanted to, like that. Then you can go back later and think about it. Okay? All right, so let's do an example, which will include, in fact, we'll even start, let's just solve a differential equation, linear constant coefficient ordinary differential equation, beginning to end. We're going to solve v triple prime equals v, okay? So this is a third order constant coefficient differential equation, right? So how do you do it? Here's some initial conditions we gave. First thing you do is you take Laplace transform. We do that. I get s cubed v of s. The s cubed should be no surprise to anybody. That corresponds, as it will from now on in your lives. S cubed means triple differentiation. This term, the s squared, that's whatever the correct way to incorporate the initial condition is. I wouldn't have known that off the bat. I would have had to go either look somewhere or figure it out. You know there's going to be some term that incorporates the effective initial condition. Minus v of s, that's the Laplace transform of this, and that's 0. I've reduced my ODE to algebra. I solve the algebra, and lo and behold, the Laplace transform of the solution of this differential equation is rational. Aha. We've just studied rational functions. Now, if I ask you now, well, the solution is the inverse Laplace transform of s squared over s cubed minus 1. What's that? And the correct answer is, I don't know. So to take the inverse Laplace transform, we'll do a partial fraction expansion. Step 1, find the poles. Well, what are the poles of s cubed minus 1? Well, the first thing you do is you remember the long story I told you about how, I don't know, where this, and there's a formula for the roots of a cubic, and it's a third of a page. Okay? So I don't know the formula. I've only seen it a few times in my life. Not relevant. Okay? Of course, if this had been 5 or higher, you could claim that, oh no, it's well known that there's no formula for it. It doesn't mean you can solve a particular one. This one's easy because, look, we know one root of this is easy. It's s equals 1. That's obvious. When you take a cubic and you divide out one root, you're left with a quadratic, and now there's no excuses. Right? So that's the way it works. So factoring s cubed minus 1 is certainly something you should be expected to be able to do, anything like that. And so finally, you get this. Here are the two roots. They are 3 roots. It's 1 and then minus 1/2 plus minus j squared 3 over 2. So we convert v to partial fraction form. So v is going to, this rational function is going to look like this. And again, just looking at the number of characters involved here, this is probably that's obviously a much more compact form than this. The difference is, though, if someone walks up to you and says, quick, what's the inverse Laplace transform of this? It's hard to say. Or in fact, it's hard to say a lot of things about this, like, quick, does v grow with time or shrink with time? Or does it oscillate? And you look at this, and until you've sort of learned a lot about it, you'd say, I don't know. It satisfies this differential equation. I have no idea what it does. Whereas down here, we'll be able to pretty quickly say exactly what it does. Looks like this. We have to find R1 and R2 because R2, this residue will be the conjugate of that one. And here we'll use, you have lots of formulas to use, or actually two good ones, and we'll use this one. B of 1 divided by A prime of 1, you work it out. It's just arithmetic. You get a third, and R2 is a third. So finally, you get this. Next step, always, so step 4b is to check, multiply this out, and make sure this is the partial fraction expansion of what you think it is. It probably is. Now we take inverse Laplace transform. We do that term by term. Inverse Laplace transform of this is easy. It's 1/3 e to the t. This one, again, it's also easy because it's just it's 1/3 e to the minus 1/2 plus minus j square root 3 over 2 t, and that's this term and that term. When you look at this and that, they both combine to become 2/3 e to the minus 2t cosine square root 3 over 2t. Okay, so in fact, that's the final answer right there. That's the final answer. And then finally, if you really want to check, you go back and you make sure that this function of time actually solves the differential equation we wanted to solve in the first place, like that. Okay? So this is that's solving that differential equation end to end. Now, in some ways, this is probably a good time to mention a few things about how all this works. It's sort of like phasors and things like that in an impedance in 101, right? That the real problem in 101 is something like this. Here's an electrical network, like a power system. And I would like to know what is the voltage and current at this point in the power distribution system. That's what I want to know. Okay? Complex numbers and impedances have nothing to do with the answer. It's ridiculous. If someone just says, I want to know what's the phase angle of the current at this point in the power system, the answer is something like minus 17 degrees or plus 22 degrees. And if someone says, what's the voltage? The answer is the magnitude of the voltage. The answer is something like it's 315 volts. That's the answer. How you get to it is kind of your own business. But the way people have done it quite effectively for a while is by transforming things, and all of a sudden complex numbers are flying around, and there's impedances, and there's this and that. People are doing complex arithmetic, and then in the end you end up with a phasor, which is some complex number. And then you translate that back and you say, okay, the magnitude of the voltage is 315 volts, and the current is leading the voltage by 15 degrees. And that's the final answer. Okay? This is the same thing. Here we have a differential equation, right here. It could represent all sorts of things: population dynamics, the dynamics of an economic system, the dynamics of a critical circuit inside a computer, the dynamics of an aircraft control system. It could be the dynamics of a suspension system, of a loudspeaker, something like that. This is what we care about, and we want to know, what does V do? And as in 101 and sinusoidal steady state, if people were smart enough to look at this, and if I could say, well, what do you think? And people could look at it for a little while and go, oh yeah, okay, I'm seeing it now. And oh yeah, I know, sure, I can see what's happening here. Sure, there's a growing term, and there's this, I'm seeing this decaying sinusoid. Then we wouldn't need all this. So everything here is sort of like our own personal, this is our own personal method for solving this, okay? From here, someone looks over, someone from another planet comes where they're smarter, and they know instantly what the solution is. They say, what, are you stupid, or what? I mean, why can't, everyone knows what this does. And then I guess the answer is yes. And they say, what are you doing here? What is all this? And what, it's just a way for us to kind of, it's a way for us to actually solve this. That's what it is. So we do this. Now what happens, like many of these things, like phasors and phase angles and all that, so in fact, if you get all the way up from there, between there and there, right, it's nobody's business. What we did here is irrelevant. It's just some side calculations we did. It's our own business. In the end, we got the solution, and you check it, and it's right. Okay? So, but like a lot of things, what, you know, up until in the 50s and 60s and 20s and 30s and so on, there wasn't any other way you were going to solve this differential equation. There was no other way, right? So the importance of all this was very high, because it's the only way you're ever going to get the solution. I mean, you'd be factoring things with your slide rule and things like that, and that kind of stuff. Okay? Nowadays, of course, this is not how you solve this differential equation. Computer does it instantly. Does it for a 500th order differential equation, right? So turns out, though, then you say, well, so why do we learn all this? And the reason is, as with sinusoidal steady state and impedances, is that once you're familiar with all this language and concepts, you actually understand this. And understanding it is very different from solving it. So what's happened recently, and it's really very, very nice for all of us, is that the understanding has been decoupled from the solution. So Laplace transform, Basers, all this stuff, all sorts of other stuff you're going to see in 101, 102, used to be important for two reasons, both computational and conceptual, right? That, in other words, that's how you decided how big a capacitor to put on some high voltage power line. That's how you decided how to build a little circuit. It was you, impedances, and your slide rule. Okay? It was you, your Laplace transforms, and your Laplace transform table. Now, in fact, the way you simulate something or solve an equation, you don't do it. People don't do it. Computers do it for us. But what they don't do yet is they don't understand the circuit or the system. They wouldn't know what to do. You can't say, hey, actually, do you mind redesigning the system so that it converges faster? Or actually, to have the current leading by 22 degrees, that's too much. So please change the power system design because it needs to be leading by no more than 5 degrees. So that doesn't happen yet. But anyway, that's the idea. Okay, so that's the big picture, and I guess we'll continue this next time.